Hello, my name is Mohit, and I'm excited to talk about our paper today titled Targeting Negative Flips in Active Learning with Validation Sets. Now, there's a lot of technical terms in there, and hopefully over the next few minutes, I'll go through all of them to make it easier to understand. Let's start by something called regression. Regression has a number of definitions in different fields, and the one that we are interested in this particular paper is something called software regression. In this slide and over the course of the next couple of slides, we'll just motivate the idea of software regression in the application of autonomous driving. So this is a scene taken out from the Kitty dataset with a number of, there's a bicyclist, there is a human being in the scene, a number of vehicles in the scene, and so on. And let's say the goal of an object detection algorithm in this case is to detect all these important objects. So let's say we are running a software, and this particular algorithm is now looking for all the cars and the different objects. It makes a decision, and you can see that most of the important features and most of the important objects within the scene are recognized, but there are a few others which are not recognized as well. For instance, there is this one car in the middle that has not been recognized, and there is a false positive as well. The algorithm says that this particular bounding box contains a human being in blue, which unfortunately is not the case in this situation. So in this kind of a setup, our goal is now to improve our algorithm, and intuitively what we do is probably update our algorithm in some fashion. That would mean that the false positive that we had, where the human being was detected when there was no one there, does not exist anymore. The car as well, which was not detected before, is being detected now. So that means there are two additional detections in our current update, which was not there in our previous update. Unfortunately, the human being who was detected previously is not detected in this particular case. Now, in an autonomous vehicle setting, the accuracy for this particular scene has technically improved from 87% in our first software constellation to an accuracy of 89%. Based on the fact that there was one false positive which was removed, while a object that was not detected, which was a car, is now detected. But unfortunately, the person that was detected in the previous software constellation is not detected right now. Even though this is the case, the accuracy has improved from 87% to 89%. So what technically has happened is that from a performance metric point of view, we have done better in terms of numbers, but a very important aspect within autonomous driving is the presence or absence of human beings in a particular scene, and our update has missed the person's bounding box in this case. So regression essentially describes the performance deterioration after a model updates. Unfortunately, regression sometimes puts model predictability at risk, and this is something that we are looking at in this particular paper. So, our goal in any machine learning model, in any machine learning algorithm, is to construct a good training data set which gives us a better accuracy. In data selection pipeline, updates generally happen quite regularly, and hence it's very susceptible to this idea of regression. So we have a training data set which was giving us an 87% accuracy. Then we collect new amounts of data that then gives us an accuracy of 89%. However, there is going to be some amount of regression that might have happened in the model that is trained on top of this data. And our goal in the paper is to mitigate this kind of regression that happens during the data subset collection. We ideally want to enable consistency in data selection pipeline, specifically for the application of something called active learning, which I'll talk about in the next few slides. There are a wide variety of influencing factors that might suggest why regression happens, and that is something that we'll discuss in the middle of this presentation as well. And finally, the last part of this presentation is going to be dedicated to a methodology, particularly called ROSE, which will help us mitigate regression while maintaining our accuracy as well. So these are the three important parts of this presentation, as well as the parts in the paper itself. All right, so let's talk about the first part, which is going to be about the definition of active learning. The goal in active learning is that we want to select the most informative samples in our training set. So let's go through this pipeline in a little bit more detail since it describes the overall workflow of active learning. In active learning, we start with this very large unlabeled data. So active learning by itself is a paradigm within machine learning, similar to supervised and unsupervised machine learning. However, the difference is that supervised and unsupervised machine learning are related to the presence and absence of labels within data. But active learning is different in the sense that we start off with a large pool of training data and we keep on adding small amounts of labeled data based on what our network feels is important for it to train. So I'll describe the process itself in this particular slide. The terminologies themselves are described within the slide as well. Let's start with the unlabeled data set, which is labeled as deep pool in this particular setting. Let's say I have access to a large amount of unlabeled data. My goal is to select a small subset of this unlabeled data, annotate that data, which will give us a D-train. Using this annotated or labeled D-train, I'll be able to train my machine learning algorithm. Let's say this is a very large-scale neural network. I want to be able to train this neural network based on a labeled subset of data. The main research question within active learning is how do I select the important data points to annotate from a large unlabeled data pool? This is given by something called the acquisition function, sometimes also referred to as query strategy. And our goal is, and the goal of any active learning algorithm is to construct a good acquisition function that helps us get a good accuracy based on a small amount of data. Going through the terminologies here, unlabeled pool is the large data set that we have. Labeled training set is the smallest subset of data that we obtain after annotation is done. A is the acquisition function that helps us move from a large unlabeled data set to a smaller labeled data set. NB is a small amount of data that is being labeled. Xi themselves are the data points, while H is the neural network. And this, very importantly, is an iterative process. In other words, I start with let's say 1 million data points to begin with. I select a small subset, about 1,000 data points to train my neural network. Now, in the remaining unlabeled data, I use an acquisition function to select the important data points and add it to my training data set. Now I retrain again with a slightly larger D-train. And this process iterates itself and it repeats itself across multiple rounds until a particular stopping criteria is reached. So, what is performance regression in this setting? So an important part in active learning is the existence of rounds. So there's round 1, round 2, and round n until a particular, or round m until a particular stopping criteria is reached. Performance regression describes the performance deterioration after a model update. So in an active learning setting, regression refers to the amount of number of rounds that exist within this process. So let's say I have round 1 and round 2. In round 1, we have our HW old, which is our classifier, while round 2 has our, I'm sorry, I think I was incorrect here. So HW old, which is our previous round's classifier, is the dashed line, while the solid line, which is our HW new, is our new round's classifier. So in this setting, I can construct for any given sample, we can have these 4 statistics. In the previous round as well in the current round, our data point was classified correctly. In the previous round and in the current round, our data point was classified incorrectly. Positive flips essentially mean that our data point was correctly classified, so it's incorrectly classified in the previous round and is now correctly classified, while negative flips is the exact opposite, which is in the previous round it was correctly classified and in the present round it was incorrectly classified. Now, hopefully it should be clear that the negative flips in this particular case are the ones that we are interested in because this is where regression comes from. So I can construct a metric called NFR, which is a negative flip rate, which basically looks at whether a positively correctly classified sample in the previous round has now been negatively or incorrectly classified, and that divides over the total number of samples that can exist. Our contributions in the paper is basically to extend this performance regression to the setting of active learning. A large part of the paper is dedicated towards analyzing this regression behavior because there are a few surprising factors that come into this. And finally, we'll be describing our method itself, which is ROSE, which is a plug-in approach that improves active learning by reducing regression across different algorithms. So let's start. So we already talked about the active learning, which is where regression fits into active learning. The next part of the presentation is going to be about analyzing regression and some surprising behaviors that it exhibits. The most important of these surprising behaviors is that NFR behavior is decoupled from generalization. So our expectation when we started looking at this particular framework is that as accuracy increases, our negative flip rate should also should decrease, which implies that as a neural network or your machine learning model learns more knowledge, it should start applying all this knowledge to existing data points. So it should remember everything it has learned and keep on classifying new data points correctly as well. So we know that if accuracy increases, by intuitively we imagine that regression is in fact decreasing. But that has not been the case. What we have seen in reality is that this expectation is not met all the time. There are going to be instances where regression and generalization, which is the accuracy, are not coupled together. Specifically, we'll analyze two things, which is class complexity and data subsets, and how regression and accuracy are decoupled from each other. Let's start with the analysis of class complexity. In this setting, let's say I'm using CIFAR 100 dataset. Class complexity analysis essentially means based on different number of classes that can exist, we are constructing an active learning workflow. So on CIFAR 10, we start removing some classes. Sorry, on CIFAR 100. CIFAR 100 has access to about 100 different classes. And once we start removing all these classes, it becomes lesser and lesser. And we'll go through the same active learning setup that we had done before. So in this particular setting, in the paper itself, we have across different classes. In the presentation, we are just showing 5 classes and 50 classes, and it should be clear here, right? So we know that across different samples, when we show on the x-axis the number of samples, as the number of samples increases, accuracy increases. However, in our expectation, we assume that the NFR decreases with more number of samples. That is the case with the 5-class setting, especially that you see over here. However, in the 50-class setting, this expectation is reversed, which is that NFR also keeps on increasing as the number of samples increases, which is in the x-axis. Right, so NFR in this particular case is situated on the y-axis. We were expecting it to decrease, but in a 50-class setting, it increases. And this is what we were talking about initially, where there is a decoupling between accuracy and NFR. In all these cases, the accuracy keeps increasing, but in 50-class setting, the NFR increases, while in the 5-class setting, the NFR decreases. So there is this decoupling. The next analysis is about subsets. Let's say I have an ideal scenario where I have access to all the labels. In that case, what I do is I take all the unlabeled pool, I construct the similar regression analysis for the present round n and n minus 1. And the entire unlabeled pool, I will divide it into 4 subsets with both correct, both wrong, negative flips, and positive flips. Again, this is an idealized case. We don't have access to either positive, negative flips, or positive flips. The reason being that the dataset unlabeled pool is itself unlabeled. So there is no definition of both correct because we don't know what is correct and what is incorrect. But if in an ideal setting for this purpose of analysis, if we have access to this particular subsets, then we are showing what the accuracy and NFR is going to look like. So in this case, accuracy keeps increasing, which is a trend that we expect. However, it's very noteworthy that the kind of subsets where and the amount it increases by is very different. So in the BC, which is a both correct phase, the trends increase with the number of samples, but it does not often lead to a high accuracy to begin with. Right? So there are other data points, let's say the red and orange, which is the negative flips and both wrong cases. These subsets, if we train our neural network based on just these subsets, they give us a faster increase in accuracy. And if we look at on the right hand side, which is the NFR, you will notice that NFR decreases for two of these cases, which is the both wrong and the negative flips, while it increases for the both correct phase, while remaining constant for the PF, which is the positive flips. Again, our ideal model has an accuracy that increases while an NFR that decreases. So in this particular case, the one that we are most interested in is the negative flips scenario. So if we were to choose a subset that is based on only the negative flips, then our accuracy would increase very quickly and our NFR would also decrease compared to the other subset where it's decreasing, which is both wrong. So this forms the major motivation for our method itself, which is going to be our regression analysis and our Rose estimation framework. So this comes to this, we now arrive to our contribution, the third contribution, where we provide a plugin algorithm to improve performance consistency within an active learning framework. So the next three slides will give a very high level overview of our method itself. So in this particular slide, I bring back the active learning workflow that we talked about very initially. The difference between the previous time we showed this kind of a slide versus now is that there is an additional rows block. Everything else in terms of the acquisition function, the labeled train set, the unlabeled pool remains the same. The only difference is that we add something called regression ordered subset estimation, which is the name of our method that only selects the unlabeled negative flips. So from the previous analysis, we discovered that negative flip rate and accuracy is decoupled. The only time it works as expected is when we are choosing a subset based on negative flips. And that's it. That's the method where instead of choosing the entire unlabeled pool in order to construct our acquisition function, what we do is only construct a smaller subset within the unlabeled pool, which is based on our negative flips. And the entire method is plug-in approach because of this reason. Because we can now use any kind of an acquisition function in order to construct our framework. So on the right hand side, on Cynic 10 dataset, we showcase entropy, the accuracy and negative flips. So entropy is in blue. The original algorithm of entropy, active learning entropy is in blue. You can notice that the accuracy is increasing and the negative flip rate is decreasing. But if we add the rows block within entropy active learning, you see the curves in orange. Again, the x-axis showcases the increase in rounds and the number of samples, while the y-axis is about accuracy and NFR. As the rounds continue, our Rose entropy keeps on increasing, while a Rose entropy increases, the accuracy of Rose entropy increases faster than entropy itself, while the negative flip rate of Rose entropy is always lesser than entropy, which basically means that we perform better in terms of accuracy while maintaining a decrease in NFR compared to the original algorithm. Regarding the algorithm of Rose itself, we have one issue. We have motivated why we use unlabeled negative flips. However, by definition, we do not know what the negative flips are going to be since we don't have access to the labels beforehand. And this is where a validation set comes into picture. We create a very simple binary detection algorithm where we basically take in our unlabeled pool. We look at all those samples that have flipped from before. Now, this flip is in fact going to be a union of positive and negative flips. We can know what data samples have flipped their labels. We just don't know if it's a positive or a negative flip beforehand. And our goal is to extract the negative flips. To do this, we construct a small validation set and have a small binary detection algorithm where, based on this validation set, we construct a binary detector that says if it's whether a data point has a negative flip or a positive flip. Based on that threshold, we say if a particular data point has been mispredicted or not. So we use this validation set to determine threshold in our misprediction detection. And that's it. That gives us our results. So there's a lot of results within the paper itself across different data sets, across different algorithms, across different architectures. In most of these results, you will see something that is very similar to what we saw in the first slide when we came to rows, where our accuracy increases faster than the base method itself, while our negative flip rate is lesser than the base algorithm itself. So ideally, our results showcase the fact that rows matches or improves the baseline algorithm in regression and accuracy in this particular case. So that brings me to the end of our presentation. Thank you for listening. And these are the QR codes for the publication code. And we have multiple other works on active learning, federated learning, curriculum learning. If you're interested, please go through our website and you'll be able to find all these publications. Thank you.